Welcome to Assignment 1U, Rational Functions and Zeros. The learning objective of this lesson is to kind of put things together for you. In this lesson, you're going to learn what causes a hole in a graph, an asymptote in a graph, and a zero on the graph. Eventually, you will learn that zeros are caused by the numerator, asymptotes are caused by the denominator, and cancellation of factors are what causes holes. With that, we can begin with example 1, which is this rational function. On top, we have a quadratic, and on bottom, we have a quadratic. And the first question we have to ask is, what is the domain? Well, remember the rule. The denominator can never equal 0. 2x squared plus 4 can never equal 0. If that's the case, then we can say that all real x's are good to go. And here's why. No matter what x I give it, whether it be negative or positive, I'm squaring it and multiplying it by 2. And this term right here will never equal negative 4. So this term will never ever become 0. And therefore, our domain is all real numbers. You can even see in the graph that there are no asymptotes. And there are 3 ways to write all real numbers. Just writing out the phrase, writing out the capital R with some thickness to it, or just saying x can be any number that's between negative infinity and infinity. Now we're going to move on to what causes zeros. In other words, why does the graph intersect the x-axis here at negative 4 and here at 2? So here's the big key for today. If you want to find the zeros happen when the numerator equals 0, when the top part equals 0. Well, the top part is x squared plus 2x minus 8. And if I factor that, I get x plus 4 and x minus 2. And when those equal 0, that's where our zeros will land. You'll notice that a negative 4 would cause this expression to equal 0. And a positive 2 would cause this expression to equal 0. And that's why we have a 0 here at negative 4. And a 0 here at 2. I'm going to introduce something that is brand new that we have not encountered before, when there is a hole in a graph. Take this rational function g as an example. The first thing I notice is I have x minus 4 in the denominator. And knowing that the denominator can never equal 0, I know immediately that my domain says that x cannot equal 4. There's nothing new there. But watch what happens when I factor out this equation. On top, I get x minus 4 times x plus 3, and on bottom, I have x minus 4. Well, when I have something in the numerator that's the exact same as something in the denominator, we say that that cancels out. And the reason why it cancels out is because no matter what x is, when I divide those two numbers, I will always get 1. That means that what's affecting the calculation is x plus 3. So g of x in many ways is really just going to be x plus 3. So let me put this rational function into Desmos and show you what happens here. When I take the quadratic function and divide it by this linear function, my result is actually a linear function. But you're going to notice that when I built the table here, the table still understands that x cannot equal 4. And it says that the function is undefined at 4. Take a look at the graph. When I go over here to 4 and I go up the graph, you're going to notice that right there, it says it's undefined. And even though you can't see it with your naked eyeball, there is a little hole here. There's a little spot that we cannot see the value. And no matter how much I zoom in, I still won't be able to see it because it's infinitesimally small. When we draw this on paper, we like to draw the hole a little bit bigger so that we can see it. So, in summary, when x equals 4, there's going to be a hole here because x cannot equal 4. What causes holes to happen is when factors cancel out with each other because these factors together just equal 1. Looking at the graph, I do see my x-intercept is negative 3. That's our 0. Because x plus 3 equals 0 when x equals negative 3. All right, let's do another example. F of x equals 4x plus 8 all over x squared plus 3x minus 10. When solving rational functions, sometimes it's useful to always just factor both sides to make sure there are not any holes. When I factor both sides, I see on top we have 4 times x plus 2, and on bottom I have x plus 5 times x minus 2. First question is domain. Looking at the rational function, I have 2 forbidden x's. X can never equal -5, and x cannot equal 2. The top is always going to tell me what my zeros are, and the denominator, what's left after cancellation, will tell me the asymptotes. Since there is no cancellation of factors, there are no holes, and you can even see on the graph that they did not put holes on the graph. Where are there zeros? Looking at the graph, I can see that there's an intersect here at -2. Looking at the numerator, I see that -2 plus 2 would equal 0. So our 0 happens at x equals -2, right here where the graph crosses the x-axis. Vertical asymptotes, those are going to be in the denominator, basically aligning with our domain. I can see here that x equals -5 and x equals 2 are the asymptotes clearly here on the graph. All right, example 4. On top we have a difference of squares, and on bottom we have a trinomial quadratic. We can factor both on top and on bottom, and what we can see here immediately is that x cannot equal 3 and x cannot equal -1, because those are the numbers that would cause the denominator to equal 0. At this point, you have to be careful. Just because this is our domain does not mean that these are both the asymptotes. The x minus 3 cancels out on top and bottom because holes happen when cancellation happens. So we have a hole at x equals 3. Zeros happen on top and asymptotes happen on bottom. We have x equals -3, which would cause a 0, and a vertical asymptote at x equals -1. In terms of horizontal asymptote, we're going back to the rules from the last lesson. We have the same degree, the same power on top and on bottom. So this number right here, whatever it leads to, is going to be the ratio of leading coefficients, which is 1 divided by 1. If you ever get confused, try plugging in, I don't know, 1,000,000 into x to see what the end behavior is. And on top, we would have 1,000,003, and on bottom, we would have 1,000,001. That's practically just going to equal about 1. So we have a horizontal asymptote, which is y equals 1. And the final thing is how do you find the y-intercept? Well, the y-intercept happens when x equals 0, and that's easily calculated. You just plug in 0 for x, you're going to get 3 over 1, we're going to get 3. Okay, one more example. This one's just a graph, and we don't have any ratio function to factor or anything. We can clearly tell that there's an asymptote here at -4, and we also see that there's a hole here at 7. So our domain is clearly that x cannot equal -4, and x cannot equal 7. Where's the hole at? Well, we already said there's a hole at x equals 7. Where are there zeros? Well, I see 2 x-intercepts here, which means we have a 0 at -2 and at 2. Vertical asymptote, already identified at the beginning, -4, that orange line, that orange dotted line. What about horizontal asymptote? Well, since my graph is going up at an angle, that's going to head to infinity. So there are no horizontal asymptotes. And we're supposed to estimate the y-intercept. That's where my graph touches the y. And it's between 0 and 1. I'm seeing something along the lines of about a half. One useful thing to do is to create a table of the different intervals of the graph and denoting what's happening at those spots. Taking a look at this here, we see that we have an asymptote at -4. So in my sign table here at -4, I'm going to say that there is an asymptote, like does not exist. That's what DNE stands for. There's no function at -4, does not exist. Same thing at 7. My function does not exist here at 7. It's a hole. The next thing I'm going to input is where I have zeros, and that's at -2 and 2. The rest of the intervals, it's asking me for the sign. In other words, it's asking me, is it positive or negative? Starting with the first interval, which is from -infinity to -4, that's this interval right here. I see that my graph is completely negative in terms of the y-axis. Everything is below this line, therefore everything is negative there. But then when it jumps to the other side of the asymptote, my graph shoots up to positive infinity, and it stays positive until my first zero. So the next zone is positive. Between the zeros, my function dips below the x-axis. I get negative again. And from this point forward, except for the hole, my function's positive and positive. Thank you for joining us today.